So let's start with the final lecture today, and today we are going to deal with mechanical design. We will concentrate on thermal mechanical problems, and first I would like to have a look at the origin of such stresses. What we can see here to the right is an assembly of many materials, a silicon chip of low CTE. It is bonded with wire bonds of copper, which have a high CTE. All of that is mounted onto an aluminum oxide plate, which has an intermediate CTE. In addition, we have a temperature distribution. In fact, it is not uniform, but we can assume here some average temperature. So during operation, just by turning power on and off, we will have temperature changes up and down, and in that way we also induce thermal mechanical stresses. When we look at stresses in, let's say, a symmetric system between two materials, which is the material P and the material I and P. So a chip in between some packaging material. That packaging material could be a polymer. And for polymers, we must say the alpha is temperature dependent, and also the Young's modulus is strongly temperature dependent. In that case, the formula which we know, which is sigma is delta alpha times delta T times E effective, is not valid anymore. We cannot just take the delta alpha for the temperature T2, but we must make the integral of all strains, and such thermal strains are integrated over temperature, and in that way the stress finally will be the integral of alpha of the packaging material minus alpha of the intermediate material integrated from starting temperature T1 to final temperature T2. And in that way, we have the possibility to compute also temperature-dependent stresses. On the other hand, when we want to make it more simple, for instance, we want to have a case where we start at the glass transition temperature, because here we can assume all of the assembly is more or less stress-free. So the assembly is stress-free either at the production temperature, for instance when we glue, or it can be assumed to be stress-free at the glass transition temperature, which is typically lower than the fabrication temperature. In that way, we can estimate the stress or the stress increase, which is again delta alpha times the Young's modulus at the lower temperature T1 times the difference of from the glass transition temperature to that final temperature. And in that way, we can estimate how stresses will be after cooling down from gluing, from soldering, or such other processes. Of course, we must know what is the relevant Young's modulus, because that is not a unique value, but that is dependent on geometry, for instance, on the thicknesses of the different layers which are involved. Also, it is important to note that when we have, for instance, soldered or glued, and we are at high temperature, for instance, T-solder, all of that is both stress-free and strain-free. When the solder is very soft and the substrate is very stiff, the chip is also stiff, the substrate will more contract than the chip, then the solder will have to take up the strain difference. In cases where we have a hard solder which couples the chip well to the also hard to a relatively soft substrate, all of this will be bent, and the substrate will typically contract more than the chip. And here we must say, for the linear part of the contraction, we will have compressive sigma, but we will have tensile bending stress. So there's a superposition, but in most cases just the bending stress is relevant here. So in that way we can try to understand the system. Of course, it is clear that on the distribution between bending portion and linear portion, many parameters have an influence, like the stiffnesses of chip and substrate, their thicknesses, and so on. So it's quite complex. But we would like to simplify the situation. So when we have a substrate, on that substrate we have mounted a chip. Again, we have cooled the whole thing after our, for instance, soldering process, and we will have stress, and we will typically see cracks here. Some of the cracks come from the top side. The reason is that here we have tensile stress. And for a brittle material, tensile stresses are worse than compressive stresses. So you can imagine you cannot open a crack by compression. No, you will close it. But by tension you will open a crack, and the crack will tend to propagate. So tensile is worse. On the other hand, we can also have cracks from the side of the chip, and that is typical a result of shear stresses in the chip. Okay, so on top tension, on bottom of course the substrate has bending, compressive stress. Okay, now in our sketch here we have two parameters of geometry which are very important. One is the length of the chip. Generally we have already made a simple model of stress development. In that model, the length of the chip has no influence. In fact, it can be shown that stresses are higher when a chip is bigger. On the other hand, also we have the thickness of that die attachment material that has an important influence on stresses which we develop, and that is clear. Why? Because the shear strain gamma is defined as as delta L divided by x. So that's the length change we have on each side, and shear generally is defined in that way. That's the displacement parallel to that plane we have here. Okay, so shear is important, and so both parameters, the length and the thickness of the die attachment, can have an effect. So of course we can clearly see that the thicker the die attachment is, the lower the shear strain will be, and of course the shear stress is just the shear modulus times the shear strain. Okay, so in that way it becomes clear that geometry has a strong effect. There is one formula you can find in a textbook, and that formula is very simple. In fact, it's not really physically too correct, but qualitatively it gives us a good impression what influences on stress level are, and that's the reason why I use this in this lecture. Of course, stress is again dependent on delta alpha and dependent on delta t. In our case here again, the Young's moduli and the alpha values are independent from temperature, but the temperature difference, of course, between starting point, which is stress-free, and end point, which has stress, is important. So, and that here is the effective Young's modulus of the assembly. And here we can say in that formula that there are two phenomena. The first phenomenon is the substrate. The harder the substrate is, the more it will try to resist against deformation, and that makes it clear that higher substrate modulus will lead to higher stress. On the other hand, if the mounting material is harder or has a higher modulus, also this will transfer more stress into the chip. So you could say the chip, for instance, will be bent more the stiffer this mounting material is, and in that way both have an influence. And also we can say that in a certain way the stress increases with the length of the chip, while on the other hand we have that inverse effect of the die attachment thickness due to this shear strain effect. And in that way we have a formula which describes the most important parameters on stress development in layered systems like chip on a substrate or chip glued onto some printed wiring board or such applications. There is one thing, there is a geometry factor C here. You can typically say this factor of C is 1 except in hard ceramic systems. So if you have a hard die attachment, for instance glass solder on a ceramic substrate, then you can take a prefactor of C is 0.1. In soft systems, like you use a glue on a printed wiring board or such a thing, you can take C is 1. and in that way you can estimate the stress in that case. In fact, we must say such cases where we have a chip on a substrate, or when we have even more layers, have been modeled quite frequently. So that's one of the, let's say, standard exercises for mechanical engineers in assembly and packaging. And for instance, Mr. Suhir did lots of work, and then he found, for instance, an iterative solution where you can say, okay, the stress on top is again delta alpha, delta t, but here you have that geometry factor which depends on certain thicknesses, t, t1 and so on, and also on some stiffness parameter, d. And these d values are also defined in a dependent on the thicknesses, on the Young's moduli, and on the Poisson's ratio of the materials. And in that way, you can compute not only the stress on top, but you could also compute the stress in every layer of that assembly. Starting from that equation, more equations have been derived. For instance, here Suhir's formula again assumes the stress is the same in if you address one surface in your assembly. There are more advanced formulas where you can also compute the stress distribution in the top surface of that assembly. Okay, that was just to demonstrate you how complex this can be made. We must also say that typically such computations are done by finite element method. Okay, in that way we have at least a method to estimate stress in systems, for instance, when we have mounted a chip on some substrate. But now let's look at another situation. Solder joints. When surface mount technology was introduced around the year 1985, people built up assemblies and they started to test these, and they found out that only after a few thermal cycles the surface mounted device just fell off the printed wiring board. And so again, mechanical engineers addressed the problem, and in that case they did, for instance, finite element simulation, and they found out that we have a strong deformation of the complete assembly. That deformation, for one, means we have some bending, we have some linear change of geometry of our BGA on the printed wiring board. But on the other hand, when you look at the solder balls, you can find that you have a strong shear in the solder balls, and here you can also see that evidently the shear strain is again larger the more to the outside of that assembly you are. And you can also find that this shear strain is larger when the device is larger. And at the corner joints we could find some of the largest deformations in shear in such assemblies. A ball grid array is something which is quite complex, and so we try to make a more simple model which has just two solder joints. Imagine we have a chip resistor, for instance, on a printed wiring board, and that chip resistor has a initial length L0, and it has a CTE alpha chip, and the board has a CTE alpha board. On the other hand, we can again see we have a solder gap here, and if we think that we have some shear deformation on the side or under the chip, then we can say, okay, what will happen? We will have the pads with the solder in between, and if we have a delta T, we have again the pads with the solder in between, and here we have a shear deformation, and that shear again will lead to phenomena which are not really desired. So again, we have that delta L here, and again we have the height here. And now let's analyze the problem. So the length of the device is the length of the board after the temperature change will be alpha board times the delta T times L0. So that's the length change. And the length change of the chip is alpha chip times delta T times L0. And so the total delta L is the difference between two lengths, or between two lengths differences, and so it is delta alpha delta T times L0. On the other hand, we must say that's a total length change. The length change per side, it's only half of this. Let's proceed. And so we can see, say, the shear in one solder joint is delta L divided by twice the height, or delta L half divided by the height. And again, that's delta alpha delta T times L0 divided by 2h. So for square components, we must say it is not that length, but it is that length here. And so we must multiply the strain with a factor of square root of 2, or 1.4 roughly. And in that way, we get the shear strain. On the other hand, in mechanics, we rather prefer to have uniaxial stress or normal stress and normal strain, which are uniaxial. And then we can say typically the uniaxial normal stress is shear stress multiplied with the square root of 3. That's a rough guess. And the strain, the uniaxial strain, is the shear strain divided by the square root of 3. Typically, the shear modulus is roughly the Young's modulus divided by 3. That's a good rule of thumb. And in that way, we can say, okay, the delta epsilon is proportional to the shear strain divided by square root of 3. And when we put that into our formula, we can see this delta epsilon, which we have in every temperature cycle, or in each temperature step, is delta alpha, delta T, L0 divided by 2, divided by square root of 3 times H, and optional times square root of 2 for square components. The rest I already mentioned. Now let's have a look at cyclic strains which are a result from temperature changes. That's an example of such a chip capacitor on a printed wiring board. Here's a copper pad, and what can we find? We can find large cracks here under the device. One of the reasons is the gap is very narrow, so shear strains will be large. But we have also other shear strains. For instance, here on the surface of that device, we can see the area that is affected by shear is around here. That can be clearly seen from that larger grain size. So that's a good indicator. When such a sample has large grains inside, in some locations, that's an indicator of large strain. Again, we can also see here are areas of large strain around here. Also, these holes are not a result of soldering processes, but these holes are a result of fatigue. So in that way, we can say we have a large strain, and after a certain number of cycles, here it was several thousand cycles between -40 and 125 degrees centigrade, we get cracks everywhere where there are big strains in our assembly. Now the question is, can we estimate how fast cracks will occur, or how fast the sample will be deteriorated? And to that purpose, my students, they performed an investigation. Here that was a ball grid array from in fact it was from a Mercedes car with Bosch equipment. And here we can see one ball. It looks very smooth. The solder joint looks very fine. The second image is not the same ball, because when you cut it once, you must take another ball. So we took it. What we could find here, there are such kinks on the surface of that solder joints, and such kinks are the first step towards a crack. Here even we see a minute crack, but here in these locations it already becomes larger. So that's after 0 cycles, 250 cycles, 500 cycles. You can see the crack length is always larger. After 1,000 cycles, we have cracks which are almost through that ball, and at 1,500 cycles it is completely cracked. So what you can do is you measure the crack length as a function of the number of cycles, and that they have done. And on the other hand, when you do this for very many samples, you can also find a dependency between the number of cycles to failure. So here that is the number of cycles to failure. Here it's not yet failed. So here, for instance, for that condition, it's 1,500 cycles. When you plot the number of cycles to failure against the strain difference. You get this curve here, and that's a fatigue curve. On the other hand, the strain difference is a result of the elastic plus plastic deformation. So we all know when we have a stress-strain curve, it goes up linearly, and then in that way. And here we can say up to here it is elastic, and from here on it is plastic strain. Here is sigma, and here we have plotted strain. And so you can say, if you have tests where you only have elastic deformation, you have this boundary curve of fatigue. So that's a normal fatigue curve, and that curve here is the low cycle fatigue curve, which is dependent on plastic strain, and that is relevant for solder joints. So the elastic deformation in solder joints is not very high, but the plastic deformation is what decides the lifetime here. And when we look at such a curve, so here we see it's a log curve, and a log curve can always be modeled with, for instance, power law here. So that is a law described by Coffin and Manson, so-called Manson-Coffin law, and that says the number of cycles to failure is proportional to a constant value, which depends on material, proportional to the strain range we have in that cyclic deformation, and depending on another material parameter. So here, let's have a look. That was our measurement. In the end, for all of the measurements, under different conditions, the number of cycles to failure was analyzed, and it was plotted against the plastic strain range, which we got from simulations. And in that way, we get a lifetime curve. That's a Manson-Coffin curve. And now the next step would be we make a regression to that curve. Here we see the prefactor is roughly 2. The exponent is, in that case, minus 1.28. So it's always negative. That's also clear, because the higher the stress, the lower the higher the strain range, the lower the number of cycles, or the lower the strain range, the higher the number of cycles. Again, all of this investigation just went to something like 30,000 cycles, and that meant it was still low cycle fatigue testing what we performed here. But why do we need that lifetime curve? Because now when we know this delta epsilon, we can estimate with that curve the number of cycles to failure, or at least the average value. And now let's go back a little. Here in that curve, we have the delta epsilon, and we assume that the delta epsilon is delta epsilon plastic. So we neglect elastic, deformation. And now we put this term here into the lifetime curve. And in that way, when we do that, we put in the delta epsilon, we get a formula which says number of cycles to failure is that fatigue parameter times delta alpha, delta t, times L0 divided by twice the square root of 3 and divided by the gap height of the solder joint, and possibly here also a factor of square root of 2, and all of that to the power of C2. And in that way, we can estimate the number of cycles to failure. So when we get a certain strain, for instance, assume delta epsilon is 0.01, so that is equivalent to 1% of strain, and in that way we could estimate the number of cycles to failure, and I will not be able to compute it now, but roughly it will be a few hundred of cycles which sample tolerates. Okay. The computer gives me a signal, it wants to quit, and so we are finished now. So today we have seen some techniques how to estimate stresses. Stresses are important because stresses can crack a device. If a stress is higher than the fracture strength, we will have a problem. And on the other hand, we have also seen the phenomenon of fatigue. That means when we have a continuous straining and unstraining of a specimen, that specimen will not tolerate it until eternity, because we will have fatigue processes, and these fatigue processes will lead to surface cracks and then to larger cracks, and finally we will have an electrical failure. And here that techniques I was showing you gives you help in order to estimate what the number of cycles it can be that your design will tolerate when you put in the proper design parameters. And also such calculations of stress and lifetime of solder joints will be part of your exam in August, September. Okay, thanks for your attention. When you're doing the exercises, and if you have questions, you can address me directly. Best is you give me a note per email. Also, if you have demand, we can make some counseling session maybe 1 week before the exam, so you can ask questions. Of course, that counseling should be also in a electronic way, so we make a Zoom session or something like this. So if you want that, you can address me and I will organize it. Okay, thanks for your attention in summer semester 2020, and see you in a few weeks. Goodbye.